of days, 3 days, the skies have been this hideous orange, reddish color. You may have seen some of those photos on the internet. So it's COVID-19, wildfires, we've got it all.
I think we could probably start it right now. It's just 1 minute, I've been told, so.
Just how to do live. इवेंट स्टार्ट कर दें।
Next 10 minutes, 51 people will come.
Yeah, it's just.
They're serious, so they can come in.
I can go live.
Can we start?
Yeah.
Okay, we'll start things officially. So hi everyone, and welcome to today's event. Just 2 seconds, actually, can you mute that because I'm worried that it'll be echo. My name is Ryan Graham. I'm a student at Queen's University Belfast, and I'm also a member of Blackbeam United Cosmos Organisation, or BMUCO in short. BMUCO is an organisation that focuses on scientific outreach, increasing scientific literacy in developing communities, and encouraging collaboration between scientists across the world. Today, BMUCO is hosting a seminar with a very special guest, Mr. Roger Hunter, the current program manager at NASA Ames Research Center and the former program manager of NASA's Kepler mission. The Kepler mission was the first mission capable of finding other habitable Earth-like planets in our Milky Way galaxy. So I'm sure that Roger has a very interesting talk in store for us today. After the talk, BMUCO will have some questions for Roger, and then shortly after that, we'll take some questions from the audience. So if you have any questions, please send them in the chat through Zoom or in the comment box of the Facebook or YouTube live stream. So without any further ado, you can take it away, Roger.
Thank you so much, Ryan, and thank you to BMUCO for inviting me today. And let me share my, can you share my screen?
Yep, I think we can.
Yeah.
Yep.
Yes, sir.
Sharing the screen.
Oh yeah, sure. You can.
Okay, yeah, I think there should be a button on your feed, Roger, that allows for screen sharing.
Yeah.
Yeah, when I click the button, it says the host disabled attendee screen sharing.
Okay, just a minute.
Oh,
Okay, sorry, just 2 seconds.
No worries.
Apologies for this.
Oh, are you ready?
Yeah.
We're just getting it set up here. We have our technical operator
Okay.
in the background.
Hello. Yeah.
I can share my t-shirt for today if you'd like to see that. It says, I can't keep calm, I work at NASA.
Nice.
Yeah. I'm tempted to take the ones.
Can you check it again, or is it still not working?
Ah, they're ready.
Oh yes.
Yeah.
Okay, I presume you can see this.
Yes.
Okay, of course, the typical NASA meatball logo before we begin. And, oh, back up. Oh, as we begin today, what I want to do, a lot of red. I don't know what happened. There's a lot of red on the screen. Let me stop sharing and reshare again. Okay, we're back. As we begin today, what I wanted to share with you, since today is 11 September, I found this photograph from the archive of the Hubble Space Telescope, and this was taken on 11 September 2009. And this is just through a cross section of the sky, only about a third the size of a full moon. And what you're looking at in this photograph are about 7,500 galaxies. And some of the red dots that you see in here are as far away as 13 billion light years. And it puts things in perspective. It also gives you an indication of just how small we are. Yeah, we're just a tiny speck floating in one little nondescript galaxy among billions of other galaxies. And it leads for each one of NASA's science areas, we have questions that guide our science. In astrophysics, there we go. In astrophysics, we have three fundamental questions that we're trying to answer. And one is, are we alone? How did we get here, and how does the universe work? And this was part of the National Astrophysics Roadmap that was updated back in 2013. It has not been changed since then. Those three fundamental questions are still there. And we're still pursuing answers to these questions in the NASA Astrophysics. And this is what actually led to one of our programs, a Kepler mission. As Ryan mentioned earlier, Kepler had one sole scientific objective, and that was to do a census of the Milky Way galaxy to determine the menagerie of planets that are out there. How many Earth-sized habitable zone planets exist around our host stars in our Milky Way galaxy? And we launched a spacecraft back in 2009, and we decommissioned it not too long ago in November of 2018 after a 9.5-year run. And after we got on orbit, of course, we go through the normal checkout activities of these spacecraft to make sure they're operating properly. And then we began to earnestly hunt for planets. And this is how we look for them. This is called transit photometry. And the Kepler mission's means of detecting them is pretty simple. You just stare at the stars and you wait for the planets to cross their stars. And when they do it, as you see in this animation, they block out a portion of the star's starlight. And you can then measure that change in brightness over time. And when you see this happen at least 3 times, and that was one of the means of validation that we use, we wanted to see this occur at least 3 times for each one of the planets that we confirmed, then you could discern the size of the planet, you could discern its distance from its host star and also its orbital period. And those are necessary for us to determine, exactly how many planets out there are in our Earth size and in the habitable zone. Where did we look? If you looked through the Cygnus constellation, this was the primary field of view for the first 4 years of Kepler. And we would actually continue looking into this field of view for the entire 9.5 years. But I'll tell you about an anomaly that we experienced on the spacecraft at about the 4-year mark. But this is where we pointed. And you look at that checkerboard pattern there, that represents the footprint of the Kepler photometer. And that's a huge field of view compared to most ground-based telescopes. It's a huge field of view when you even compare it with Hubble's telescope view, because we intended to look at a wide field of view so that we could collect data on many stars. We needed to collect data on many stars because we were doing a statistical sample. We wanted to understand the prevalence of these planets. And so you need to survey many stars. And so during the first 4 years, we looked at about 190,000 stars in that field of view. So let's talk about results. This is that same field of view, a little bigger close-up of it. And of course, the white material you see here, those are all stars and galaxies. The field of view is just covered with stars and galaxies. And the 3 yellow dots you see there represent the known exoplanets, planets beyond our solar system that have been detected by other means, likely radial velocity. And so we knew those were in the Kepler field of view. And as we continued to collect data on a monthly basis, as we observed for the first 4 years, looking through this field of view, we began to find planets and we began to characterize them and we began to categorize them. And after 4 years, this is what we had detected so far. We have over 4,700 planet candidates in that field of view. And you can see a legend on the left side in which we started characterizing the size of the planets. There are many Earth-sized planets, of course. We picked the pale blue dot in homage to Carl Sagan, of course. And then you can see the other planets that we detected in this field of view, from the super Earths, the Neptune-sized giant planets. We did find planets as small as the size of our own moon. And we also found planets that are much bigger than Jupiter. But we were, in some sense, we were astounded by this, but was also just affirming what we believed before, that, why would we think that our solar system is the only planetary system out there? Why would we think we're that unique when this cosmos that we live in consists of billions of galaxies, and this galaxy that we sit in, the Milky Way galaxy, has 200 billion stars plus or minus itself, and we think that we're the only planetary system? How arrogant are humans when we think that? There's one thing I want to mention to you, and that is, I alluded to this earlier, and at around the 4th year mark of the Kepler mission, we experienced a malfunction on the spacecraft, and we lost one reaction wheel, a gyroscope, in the 3rd year of the mission. And we lost a second gyroscope in the 4th year of the mission. And there's 4 of these on the spacecraft, and need 3 to provide the precise pointing that we needed to allow us to conduct the precision photometry with Kepler against that original field of view. And you can see that original field of view up there against Cygnus, the Swan constellation. Well, when we lost a second gyroscope reaction wheel, we had to come up with a different means of pointing the spacecraft. Actually, we thought we were dead in the water for a while, but then some enterprising engineers realized that we could actually use the wind pressure from the solar wind against those solar panels you see there, and let the solar wind act as a balancing wheel with the 2 remaining reaction wheels, and we could still point the spacecraft with enough accuracy that we could still find planets. Albeit we could not point at the original field of view, we had to point around the galactic plane, and the ecliptic plane. So you see those other footprints that you see, and you can follow my cursor. We ended up pointing Kepler along that plane, and we had to move it every 8 days, or every 85 days or so. And when we did that, we were still able to find planets in that field of view, the new fields of view. And so we continued to detect planets, albeit we could not stare at the original field of view. And so that still contributed to the results of Kepler. We used this to find other planets, throughout the galaxy. And we also, in many cases, in one of those campaigns that you see, we actually targeted far away galaxies to see if we could detect supernova within those particular fields of view that we were studying for that 85-day period. So I'm not sure where the blue lines are coming from. Is there a way that you could erase those, Ryan, or should I stop sharing and reshare again?
I guess you could reshare again, that might get rid of them.
Yeah.
Okay, let me stop sharing and I'll reshare again. Okay, we're back. So, sorry about that. I think they may have resulted when I was moving my cursor around. But this is what we found. This is the final Kepler mission counts. And I pulled these off of the website not too long ago. And so this gives you an idea of what we have found so far. And of course, you see there at that number on the bottom, in the middle on the right, the 4,700 plus total candidates and confirmed planets. And so we're still in the process of confirming planets. And I'll show you an article in a moment in which there's one enterprising group is now using machine learning to help us confirm the planets. We've confirmed over about half of those 4,700, and we're in the process of confirming more. But there's another number I want to bring to your attention. It's sort of in the middle of that table on top. It says candidates and confirmed in the habitable zone. And you can see the numbers, 361 planets that we have confirmed to be in the habitable zone area, which you get the same insulation that Earth gets. And so we think that's where we would find water able to pool on the surface of the planet. Now that isn't an assumption that water is a necessary ingredient for life. It is on this planet, so we're making that assumption that it is for others. And Bill Barucki, who was a principal investigator for Kepler, he and David Koch basically said, we need to go find the planets that are at the right distance from their host stars that water might be able to pool on the surface of the planet. It's not too hot, it's not too cold, it's kind of like the Goldilocks zone. And so that's how many we found that are candidates and confirmed in the habitable zone, and a number of those are Earth-sized planets in the habitable zone. I think is close to, but if I remember my numbers correctly, it's close to 3 dozen now, thereabouts. And I think there's more going to arise as we look further into the data, because the data are still there being investigated, and the Kepler data set is probably going to be a treasure trove for astrophysicists and exoplanet scientists still for years to come. This is what we got out of the K2 mission. And this is, as I pointed out, we were still able to point the spacecraft even after we lost 2 reaction wheels. And we were able to find a number of planets, even in those new mission fields, even though we could only observe about 85 days in each one of them, because as Kepler was moving, as we were pointing at the new fields of view, every 85 days, we had to repoint the spacecraft to avoid sunlight getting into the barrel of the telescope, because if it did, the photometer is so sensitive that you would have just destroyed the photometer. I think I hear some background noise. So, and finally on the next chart.
Could I just say to anyone who's watching the stream, if you can turn on the camera and audio, that would be really great.
Okay, this last chart gives you the summary counts right. These are confirmed planets. All exoplanets is 4,100. You can see that a number of these were found by Kepler, and of course, there was a follow-on mission to Kepler called TESS. Kepler was meant to look deep and into one particular part of the galaxy during its entire mission. Of course, we had to repurpose it after the second reaction wheel failed, but we still were able to continue, as I mentioned earlier, find planets using Kepler. But then another mission called TESS was launched using the same sort of modus operandi, using transit photometry to find planets, but it was looking closer in at our own stellar neighborhood with up to about 35 to 85 light years out. And it found a bunch of planets as well. And so if you want to look into the TESS database, there's a number of candidates even within TESS that remain to be confirmed. So both Kepler and TESS, prolific exoplanet discoverers, and they have confirmed a number of the planets. And so this is where we get some of the statistical analysis. I mentioned to you the other day that now there's some group that are using machine learning to find planets within the Kepler data. And this is at a University of Warwick, and they released this news event, and I found this fascinating. And this was not long ago, they released this, just a few weeks, and it said 50 new planets were confirmed using machine learning as they started applying their own algorithms with machine learning to look through the Kepler data set. And so I'm sure that there will be others that will continue to investigate and analyze the Kepler data, particularly for those candidate planets that are not yet confirmed. And there's a possibility that there will be other planets that will arise from the data set that are not candidates now. I'm sure that there are going to be other discoveries that are made from the Kepler data set as people continue to apply even more elegant and sophisticated algorithms against the Kepler data to discover more planets. And we got the blue lines again. Let me stop sharing and resharing again. Okay, we're back. So now we're back to and talking about what is the occurrence rate of Earth-sized planets in a habitable zone. And this is what we set out to find. And I put some information here from 2017. Some of the scientists who was working with Kepler did an analysis of the Kepler data set. And there's two numbers on here that stick out. And you see the 0.6 for half Earth size up to 1.5 Earth size with those particular orbital periods of 237 to 864 days. That sort of puts them in the habitable zone. And then there's another one at the bottom, the 0.41 occurrence rate per star. Those were stunning numbers to me when I saw those back in 2017. And to put those simply, the first number, the 0.6, means that 60% of the stars, when you go outside and look up at the sky at night, have Earth-sized planets in a habitable zone. And the bottom one says, if you want to take a more conservative approach, about 41% of those stars have Earth-sized habitable zone planets in them. Now, there's another paper that I've just seen recently, and I was asked to co-author, and I did put my name to it, but there's many more scientists that are much more astute at exoplanet science than I am, and I was honored to be included as part of the co-author set. And this is going to be released really soon, and it's sort of consistent with these numbers that you see here. We used to say conservatively before this number was released that you see cited here, to be conservative, we would say go outside at night, look up in the sky, every fifth star you see has an Earth-sized planet in a habitable zone. And then these more liberal numbers were published. And now more analysis has been done, and we are starting to see that it likely is more along the lines of these liberal estimates for this occurrence rate. And I think when this paper gets published, it's going to be along the lines of go outside, look up in the sky, and then when you start counting the stars, 1 out of every 2 stars has an Earth-sized planet in the habitable zone. And we got the blue lines back. Let me stop sharing and I'll reshare again. Not sure what's going on with that, but we'll get past it. So that is the main result that I want to share with you from Kepler. It's been an astounding mission. And I think when a final legacy for Kepler is written, I think it's going to be considered one of the great observatories up there with the Hubble Space Telescope, and be considered one of the noble missions that NASA has conducted. Of course, it's, everybody, of course, remembers Apollo, and no one can ever eclipse that, at least for now, until we start working on Mars. But it's one of those amazing missions that has fundamentally changed our understanding of the cosmos and the menagerie of planets that are out there, and what we know about the cosmos now, as opposed to when we started looking at the skies hundreds of years ago with Galileo's telescope. Planets are common. They far outnumber the stars. And Earth-sized habitable zone planets are relatively common too. And so this is the foot stomper that I would take away from the Kepler mission, is these two main bullets that you see on this chart. It has been rewarding to have been part of that mission, and people still talk about it. I think people still are amazed by the Kepler mission. And even now, I think there's still scientists that are still plowing through the Kepler data to look at this data set to see what else they can find. There are a number of supernova that we characterize with the Kepler mission, particularly when we got into what we call the Kepler K2 mission, when we were left with just two of the reaction wheels or two of the gyroscopes left in the mission. And we were using the solar wind pressure to help balance it and point at other parts of the galaxy. We found over 61 supernova, and so those are in the Kepler data set now. So it has been an astonishing mission from beginning to end for just exoplanet science, but also for astrophysics. And this is one of the last images that Kepler took. We were about 93 million miles away from Earth, and we wanted to do a farewell image because we knew we were getting to the end, because we were running out of propellant. And the propellant is not used for propulsion, it was used for helping desaturate the reaction wheels on board the spacecraft as it pointed. And so we imaged the Earth. And of course, the photometer is sensitive. It shows up as a very bright streak. And you see the Earth-Moon system there in the middle of that, but that bright streak is caused from the circuitry of Kepler, because the light was so bright, it excited the circuitry on the photometer. But this is the last image we took. Now, there's one thing I would ask those of you on this event today. I may or may not have mentioned the orbit that Kepler is in. It is in the heliocentric orbit, just like Earth, and we set it into an Earth trailing heliocentric orbit. It takes us just a tiny fraction over 365 days to go around the sun every year, and it takes Kepler about 371 days to go around the sun. So we're like two runners going around a racetrack, and Earth is a little bit faster. So what does that mean? That one day Earth is going to lap Kepler, and we want you to go get it. And matter of fact, we even know the date, September 25th, 2060. Earth is going to go right by Kepler, and I put these funny little cobwebs on it to indicate its age at that time. It's going to be like a relic in space. But we're going to go right by it, but it's going to be quiescent because we turned it off. We turned every subsystem on board the spacecraft off. And so it's going to be a quiet, dead spacecraft when Earth goes right by it. And I'm hoping that you will have the technology in 2060 that you guys can go up and retrieve it and bring it back and put it in an appropriate museum, because it has fundamentally changed our view of the cosmos and affirmed what we believed when it comes to planets beyond our solar system. Now I'm going to switch gears on you. Currently, after I left the Kepler program as the program manager over there, I became the program manager for NASA's small spacecraft activities, particularly when it comes to space technology development. And I'm going to talk about the column on the left, but NASA is starting to embrace small spacecraft to conduct science and exploration missions. The two columns you see on the right, and we're just getting started in this, and we're starting to embrace small spacecraft because of the revolution in electronics area for all of us, because as we've gotten better at building electronics devices like the smartphone in your own pocket, we're starting to use those technologies to embed them in spacecraft to allow us to build smaller spacecraft that do, in some cases, just as well as larger spacecraft. So we're doing that today, and we'll continue to do that for the years to come. And my job in that column on the left is to bring the technologies that are being developed today, whether they are by NASA or other government agencies, by academia or small businesses, or by large businesses. And we're bringing those up through their technology readiness levels. We're maturing them and getting them ready so that they can actually be used in science and exploration missions. So what does my office do? We are expanding our capabilities to execute unique missions through rapid development and demonstration of small spacecraft. And this object you see on the right on this chart is a actual spacecraft that we built with the Aerospace Corporation. And to give you a sense of its size, it's about 10 by 10 by 15 centimeters, so 1.5 U, with one U being 10 by 10 by 10 centimeters. And because of the revolution in the electronics industry, we think this is going to help us lower the cost and reduce the time it takes to build these spacecraft, and also enable new mission architectures. And we want to get to the point where we can extend the capabilities of small spacecraft so that we can reach new destinations. Small spacecraft today are basically hostage to low Earth orbit. Go look at the company that's called Planet. All of their spacecraft are in low Earth orbit, and they are using spacecraft the size of a loaf of bread, about 3U, to observe the Earth 24/7. NASA's interests, of course, extend beyond low Earth orbit, and we want to get into cislunar and planetary space with small spacecraft. And so that is the job of my office, is to further the technology development in propulsion, power, communications, and processing, so that we can reach those new destinations in cislunar space and also planetary space. And there's just, I want to give you just a sample of some upcoming small spacecraft activities that we are using to demonstrate technologies in low Earth orbit before we put them in cislunar or planetary space. PTD on the left, the Pathfinder Technology Demonstrator, that's a 6U spacecraft. And on the bottom of this chart, I listed some of the technologies that we will put inside that spacecraft to demonstrate them before we put into a cislunar or a planetary space mission. There's a water-based thruster, there's a new attitude determination control system. We're going into higher bandwidth laser communications, or a demonstrated laser comm with small spacecraft from low Earth orbit at 200 megabits per second. And with item 3 there, you see on the bottom, we're going to get up to 200 gigabits per second. So we're rapidly improving the capability of the communications for these small spacecraft by moving into the optical comm area. The one on the right is called CPOD, CubeSat for Operations, Proximity Operations Demonstration. This is the first time we're going to show 2 small spacecraft, also 3U in size for each, and they're going to do proximity operations around each other and do autonomous docking. We think this is necessary to demonstrate the ability for objects in the future that we can assemble large apertures in space using smaller components, and we can do it autonomously. So we're doing the fundamental research today that will enable us to build larger apertures or larger objects in space in the future by using smaller objects that will self-assemble or be guided by some sort of autonomous operation. This is just another list of upcoming U-class demonstrations. All of these within NASA are launching within the next year and a half. There's a new solar cell activity that we're working on, advanced composite-based solar cell. That one you see on the left is going to be about 81 square meters when it unfolds, but the technology is in the composite booms that will be used to unfold the cell and give it form so that it can sail through the solar wind. And the composite booms are an improvement over metal booms because they don't warp and twist in the radiation environment of space. And the next one, Starlink Distributed Spacecraft Mission, we're showing that we can use small spacecraft in a swarm, and all spacecraft can talk with one another, they can coordinate with one another, they can also fly in formation with each other. We think this is important to use a larger number of spacecraft when we go after a science object of interest in the future. And that swarm of spacecraft can do multi-point science data collection against a science object of interest, and all the spacecraft are communicating with each other, and they can share data, and they can provide a better resolution of what the science object of interest is doing, or give us a better characterization of its composition. We're also going to work on some other demonstrations that are coming up. We've demonstrated laser comm by small spacecraft to the Earth already with another experiment. Now we're going to show laser comm between small spacecraft with another mission called CLIC. This one also launches within the next year and a half. And one on the far right is called VREX. It's just another demonstration of small spacecraft operating a swarm, and this one is going to demonstrate autonomous ranging among the spacecraft. So this is just a quick hint of some of the things that we're working on that will allow science and exploration missions to be enabled in the future using small spacecraft. Two that I think are key for us are the two that are depicted on this chart, Capstone and Lunar Flashlight. We're getting ready to build a next space station. It's called Gateway, and it's going to go into a special orbit between the Earth and the Moon, and it's called a near rectilinear halo orbit. We've never flown in that orbit before. And Capstone, which is about a 12U size spacecraft, we're launching this in April of next year, and we're going to put it into that near rectilinear halo orbit. And we're going to be doing ranging operations between the spacecraft and the NASA Deep Space Network on the Earth, and also a spacecraft that's orbiting the Moon today that's called the Lunar Reconnaissance Orbiter. And that ranging between those three entities will allow us to fully characterize the near rectilinear halo orbit before we put the Gateway space station in it, because we want to make sure that that orbit is as stable as mathematics tells us that it is. On the left, Lunar Flashlight, a 6U size spacecraft that will be dropped off around the Moon after the Artemis launches the new SLS, or Space Launch System, our new rocket that we're working on, when it launches late next year. And this Lunar Flashlight is going to be dropped off around the Moon as Artemis is taking Orion, our new space capsule, around the Moon on its shakedown, or its maiden voyage. And Lunar Flashlight will then illuminate, using a special laser head, all of the dark craters around the South Pole, because we want to get an idea of the prevalence of water ice in the bottoms of those craters. So now we're seeing spacecraft moving into cislunar space and actually, in a sense, conducting science, even though both of these are technology demonstrations. The Lunar Flashlight, I think, is still going to give us an idea of the prevalence of water deposits around the South Pole, even though it's still just a technology demonstration for us. So that was a quick overview of what we're trying to do in small spacecraft technology. We think we can use these small spacecraft to augment or conduct separately science missions and exploration missions for NASA in the future. And we are advancing some early demonstration technologies that will reduce the risk for us to conduct these missions in the future using small spacecraft. Now, I mentioned, and Ryan mentioned this earlier, I was going to touch on some other items that I think are of interest to you. Everybody, not everybody, but most people are aware of the Crew Dragon maiden voyage earlier this year. And the photograph you see on the left is, of course, Crew Dragon on top of the Falcon F9 rocket at Cape Canaveral before it launched. And the image you see on the right, actually, that's an artist drawing, even though it looks real, of Crew Dragon that was approaching the ISS. But I do have real photographs of it on orbit. And this was taken by one of the astronauts that was on an extravehicular activity outside the International Space Station. And you can see Crew Dragon docked to the International Space Station with its front door open, so to speak. And this next image shows you, I love this image because it shows the Crew Dragon firing its thruster as it's getting ready to depart the International Space Station. Coming up later this year, the second mission for Crew Dragon, and this is, the first one is called Demonstration Mission 1, but now this we're going to go operational, and this was going to carry 4 astronauts up to the International Space Station. I think the launch date is scheduled for October, but I'd have to check on that. But I was amazed when I saw this photograph how spacious this thing looks. Of course, you can do a lot with fisheye cameras to give the impression of spaciousness, but it's a change in the way that we have shuttled astronauts to orbit. And we've gotten a little more futuristic looking in our designs. And it made me think of the days, early days of space exploration. This was John Glenn, the first US astronaut to orbit the Earth, being crammed and shoehorned into his Mercury capsule. And that's not very spacious at all. Then you can see this comparison of how we have changed the cockpits of spaceships over the decades. And you can see Apollo 4 back in 1967, the Space Shuttle in 2002. And then there's Crew Dragon in 2020. It looks almost like a set out of that movie 2001: A Space Odyssey. And this is a comparison of the Soyuz capsule on the left. You can see the 3 cosmonauts crammed into the Soyuz capsule. And then on the right, there's Crew Dragon, and that's Elon Musk sitting there inside the unveil of the Crew Dragon capsule. Coming up, I want to make sure you're aware of 2 more that are going to be demonstrated late this year or early next year. The one on the left is another crewed, CREWED, crewed as in it carries people. This is the Boeing version that's going to be used for sending astronauts to the ISS, but also shuttling supplies to the International Space Station. And NASA is also teamed with the one on the right, a company called Sierra Nevada Corporation. It looks like a sports car version of the space shuttle, but it is this one is only used for cargo transport to and from International Space Station. And this one is going to launch later this year. So there's 2 other capsules coming up that I think would be of interest to you if you're keen on how we're sending astronauts to space for low Earth orbit or shuttling cargo back and forth between Cape Canaveral and an International Space Station. Now let's talk about Mars for a minute. Not too long ago, the Perseverance rover launched toward Mars, and it's an upgrade over Curiosity, which launched toward Mars in 2012. But there's some interesting things about Perseverance that you may or may not be aware of. We're taking along a miniature helicopter for the Perseverance rover, and I'll show you an animation on that in a minute. But we're about to have what I call the Wright brothers moment for Mars. It'd be the first time that humans have flown an aircraft through the atmosphere of another celestial body. But where are we going? This is what I want to talk about. And this is a colorized version of Jezero crater. And there's an indication that there was an ancient lake in this crater. And this is, of course, a colorized version photograph of the crater itself. And it's not that little dimple that you see in the lower right-hand side. The crater is this huge area, and you can see these ridges on the left that if you can see my cursor moving, that's the outline of the crater itself. And you can see this alluvial plain. It looks like a river had flown into this area in the past. And so let's take another look at it from this perspective. And the whole big bluish, purplish areas you see here is the Jezero crater. And you can see there's other little craters inside it. And the black ellipse that you see on the left, that's the area that we're going to attempt to land in. But what's fascinating about this is you can see this canyon-like part on the upper left-hand side of this photograph, and it looks like a river. It cut through there at one time and flowed into this, apparently this old paleo lake. And you can see on the right side an exit area. It looks like water was flowing out of it as well. So this is the reason we're going into Jezero crater. And this photograph here you see on this particular chart, of course, on the lower left-hand side, you can see Mars, and you can see the little gold circle represents where Jezero crater is. And the white dash marks you can see is that ellipse that I showed you on the previous chart. And the yellowish goldish color trail that you see there looks like it's snaking along like a piece of string. That is the notional path for the Perseverance rover. And that's where the scientists, I think, are planning to move it. But this is just a notional path right now. I don't know what their final plans are. But this is where it's heading when we land in late February of next year. And of course, when you go through the checkouts, this is when it starts its journey along that string-looking version there. There's a different landing technique for this one as opposed to the 2012 landing of Curiosity. Because we're coming in so close to those ridges, we've added some updates and upgrades to the landing mechanism for Perseverance. And as it gets close to the surface of Mars, it's going to do a very quick terrain mapping to see where it is. And if it's over the ridge, it's going to be able to divert with the sky crane and land in the ellipse. So there is going to be some autonomy, of course, that the rover and its deployment mechanism is going to use to make sure it doesn't land on the ridge itself, because we want to divert into that crater. So if you're keen on watching it, if you go back and look on YouTube, there is some great animation that talks about the landing of Curiosity back in 2012, and it's called 7 Minutes of Terror. Well, this is an updated version, an upgraded version of the way we landed Curiosity back in 2012. It's kind of a keen and intriguing and amazing video. So let's talk about this helicopter. You can see the technicians working on this before it was loaded onto Perseverance rover. And now let's look at some animation. And we're going to do this early in the mission for Perseverance after it lands on the surface. And it's going to be deployed from underneath the rover, and then the rover is going to back away from the helicopter. And this thing is solar powered. And we had to build it so you can operate in the very thin atmosphere of Mars. Mars's atmosphere is much thinner than that of Earth. And so this thing is going to rotate around 2,400 RPMs after it charges up. And we're going to do some initial tests with it, in which it's going to do just some up and down flights, maybe go up to 5 meters, back down to the surface. Another test, 10 meters above the surface, then back down. But this animation you see here actually combines all of them at once, because we want to make sure that you could see this thing operating. And after it charges up enough with its solar cells, it's going to rotate counter rotators, blades for the spacecraft, aircraft, I should say. And then it's going to lift off and fly around a bit through the Martian atmosphere. This is a technology demonstration. It is not meant to conduct science. This is just a technology demonstration. They're just going to have a camera board because we like to see what we're doing. But as it lifts off, we're actually going to be following it with the cameras on board the Perseverance rover, and you can see the reflection inside the camera eye. And I'm hoping that we're going to be streaming this, even though there's an 8.5 or 9 minute light time delay between Mars and the Earth. But this is, again, as I mentioned earlier, the first time we're going to fly a aircraft through the atmosphere of another celestial body. We'll let the animation run to the end, but this represents a collection of the different maneuvers that we'll be conducting with Ingenuity. That's the name of the little helicopter, as it's flying it through the atmosphere. After it completes a couple of its runs, of course, it will run that to the surface, because the batteries, I think we'll give it several minutes of flight time, and then we'll come back and we'll recharge again. And then we'll conduct a couple more flights with this. But I think I'm looking forward to this particular aspect of the mission. Now, there's one other thing I'd like to make you aware of about Perseverance, because you can see these other devices being loaded into the belly of Perseverance, and those are collection tubes. We're actually going to be collecting samples from different parts of Jezero crater, and we're going to cache those in a particular area of the crater. And on a future mission that's being developed now, we're going to Mars, and we're going to retrieve these collections and bring them back to Earth for analysis. So that's another aspect of Perseverance that I'd like for you to be aware of. Now, here, I'd like to bring to your attention another mission that's going on right now, and there is a spacecraft that's orbiting the asteroid Bennu, and this is called OSIRIS-REx. And this is a artist depiction of that, and we've been orbiting this asteroid for a little while now. But October 20th of this year, we are going to touch this asteroid with this collection device that you see extending down from the bottom of OSIRIS-REx. And when we touch it, we're going to blow a cold gas through the collection device so that we can blow debris and surface material of the asteroid into this collection device. And then we're going to put it into this little hat, this conical shaped collection pod that you see on top of the spacecraft. And after we think we've collected enough material, the spacecraft is going to do a turn and burn and come back to Earth, and it'll depart the asteroid in March of next year. And it's going to take about a little over a 2-year trip to get back to Earth from that distance. So this is coming up later this year. It's October 20th. And so I'm looking forward to that event for another NASA mission that's ongoing today as we speak. And this picture here is another high resolution image of the surface of the asteroid. And this darkish, wet looking spot that you see on the lower right-hand corner, just atop of that is where we're going to do the collection. And just to give you a perspective on size, this boulder you see to the left of that wet spot, that's about the size of a school bus. Other missions that are coming up, James Webb Space Telescope is going through its final assembly, integration, and test activities at the Northrop Grumman facility, which is down near Los Angeles and El Segundo, California. That is supposed to launch late next year as well. And of course, Artemis, our new big rocket, which is the powerful replacement for Saturn V, is under development. And this is also supposed to launch late next year. And so there's a number of important missions that are coming up for NASA that we're going to be conducting in the coming year and a half. And I'm just giving you an indication of those, but I want to show you this one more mission. We're learning some things from the technology demonstration of Ingenuity, the helicopter that's going to fly through the Martian atmosphere. This is another mission that NASA has approved. This is called Dragonfly, and this is just an animation of this particular spacecraft, aircraft, that we're going to launch to Titan, the second largest moon in the solar system, in the year 2026. It'll take a few years to cruise out there, but we're going to deploy this into the atmosphere of Titan, and then we're going to fly through the atmosphere of Titan with this quadcopter. Now, this is nuclear powered. Of course, you see that sort of cylindrical device on the back end of the landing craft there. That's where the nuclear power cell is. But this, every night, this thing will land, or after several many hours, and it recharges the batteries using the nuke on board, and it flies some more, and it's going to be conducting some science through on Titan, flying through the atmosphere and landing on parts of Titan. So I just want to make sure that it brings this up to your attention, so it's something to put on your horizon. But this is still 6 years away from launch, and it's going to take several years to cruise out to that moon later in the early 2030s. So I just wanted to bring that, that's my presentation for most of the day. We talked about Kepler, and I wanted to make sure that you had an understanding of where we are with the results from the Kepler. It's been an amazing exoplanet mission, and helping us characterize and catalog the menagerie of planets that are out there. It is amazing how many Earth-sized habitable zone planets have been discovered, and also the results that are going to be published in the near future, which gives us an occurrence rate for what Kepler has found. And so that's where I wanted to leave you with Kepler. And then I mentioned a few things about NASA's small spacecraft technology development. We are embracing the use of small spacecraft to help us conduct the science and exploration missions for the future. Of course, large, great observatories will always be part of the NASA tools to help us understand the cosmos and continue to peel back the onion to understanding some of the answers to some of the fundamental questions that we're still asking. Are we alone? How do we get here? How does the universe work when it comes to astrophysics? And then I just wanted to give you a flavor of some missions that are coming up, including the launching of some new capsules that are going to the International Space Station, and what's going on with the Perseverance rover, and also make sure that you're aware of OSIRIS-REx. And we're going to be bringing a surface sample back from an asteroid early next year after we do the touch and go with that spacecraft against the asteroid Bennu in October of this year. So I'll conclude there. I think some of you had some questions. I know that the board sent me some questions, and one had to do with the Fermi paradox. And people could be asking if there's 200 to 400 billion stars in our galaxy, and given the occurrence rate of Earth-sized habitable zone planets, if the galaxy is teeming with life, then why haven't we made contact with them? And I found this chart, I found it was interesting, and I can send this to you, but it's why haven't we made contact? And there's several answers or several possible answers here, some of which are, space is too vast and maybe we will never be able to contact anything. Maybe the civilizations that exist or possibly have existed throughout the cosmos, they've already destroyed themselves one way or another. There are other speculations that maybe we don't know how to talk to one another. Maybe we don't communicate on the same electromagnetic spectrum that we understand that they do. No one really knows. I don't have a good answer for you, but I know there's a lot of people that speculate about it. I discussed this with Frank Drake himself, who is the guy who basically came up with the Drake equation because he visited us one time on Kepler. So he's fascinated, of course, with SETI, because he is a part of SETI, the search for extraterrestrial intelligence. And there are a lot of potential answers to it. I and many others, we just don't know the answer to that question. Where are these other civilizations? Why haven't we made contact with them? Will we ever make contact with them? Good questions, but I don't think we have a good answer for those yet. So Ryan, I'll stop there and see if there's any other questions you want to talk about. I have a couple more charts if we go down to the path of where we are with the industry.
Yeah, well, thank you very much, Roger. That was an extremely interesting talk, and I'm sure that everyone got a lot from it. I'm just going to pass over to one of my board members, and he can ask a question.
Hi, this is Rajesh here. So I'm board member at BMUCO. So I wanted to ask, what do you think is NASA's one of the biggest goal that NASA wants to achieve, and so far it hasn't done much on it, something that for the coming decades, it's one of the NASA's plan.
Well, that's a good question, but I would say there's a number of objectives, and you would have to look in each one of the roadmaps that we have for each one of our science areas. Of course, we have earth sciences, we have heliophysics, the study of our own star, we have astrophysics, the study of the cosmos, and we have planetary science, the study of our solar system. And so you probably remember the chart I showed earlier in the presentation today, which are the three fundamental questions that drive astrophysics. Are we alone? How do we get here? How does the universe work? And every one of those roadmaps that we have, and there's 4 of them, there's fundamental questions in each one of those. And so we're still trying to answer those questions. I just mentioned one today. The one that I think is of keen interest to everybody, of course, has to do with earth sciences. And we're trying to understand the growing impact on this planet of climate change. That is an existential crisis for us. And NASA is interested in observing the Earth, as we always have been, to understand the transport mechanisms of our climate, but also this biosphere that we live in. And I think your generation is inheriting a planet that is in danger. And there is something that NASA is trying to do everything it can to understand the impact of our emissions and our impact, the human impact on this planet. We are living in, I think, what some people call an Anthropocene era. Climate change has an anthropogenic element to it. I think that science is settled. The question is, what are we going to do about it? Of course, NASA is working with not just our federal government, but our partners across the pond with the European Space Agency and with the Indian Space Agency, and I think with others, ISRO, to further understand the impact that we're having on this planet and what does the science tell us that we can do about it. Of course, we have other missions ongoing today to understand more of the behavior of our own sun, heliophysics, with the Parker probe. We have others that are coming up as well, but I wouldn't say there's a singular theme that NASA is focused on. We are focused on so many different areas, and we're trying to get some answers that we can provide decision makers to help them guide their policies so that we can be good stewards, not a planet, but good stewards of science, because we want to still answer fundamental questions. And even when we answer those, more questions will arise. So I don't know if I really gave it the answer that you're looking for, but those roadmaps that we have are guiding the kind of science that we're conducting today to help humans live well on this planet. And then as we extend our presence into the solar system, that we understand how we're going to do that.
Okay. Another question we have from one of the viewers, Naman, is when we're looking for other forms of intelligent life, we're basing our search upon looking for qualities that exist on our Earth. So I guess we being carbon-based life forms, the presence of water. So I guess the question being posed is, could there potentially be other life forms that are out there that perhaps aren't carbon-based or don't need water to survive? And could it be possible that those life forms are just existing under our noses?
Yeah, I understand the question. Interestingly enough, Ryan, I had the same conversation with Dr. Elizabeth Blackburn several years ago. And she's not an astrophysicist. She has a Nobel Prize in medicine. And I encountered her in an event here in the Silicon Valley, and we got into this discussion. She was very keen on Kepler, and this is in the early days, and we were 3 years into the mission. And we met on this convention room floor, and we talked for a while about this. And she raised the same question. She says, don't you think it would be interesting if we found life forms that were based upon something other than carbon? And I said, like what? Like silicon and boron is what she brought up. And I said, I don't deny the possibility, because every time we look every time we are asking ourselves some of these questions, we are surprised sometimes with the answers that we get. I said, but we also have to look at it from the perspective of when we turn our instruments onto the heavens, we see so many of the same elements that we see here. And you go look at the periodic table, it says hydrogen, helium, oxygen, carbon. And carbon is one of those funny elements that combine so easily with so many other elements. And we sort of agree that it's likely to be carbon-based, but that doesn't mean that it will be. It may not be, but more than likely, it probably would be, because of the way carbon combines with so many other molecules so easily. But because I said, look at the diversity and abundance of life on this planet, and all the carbon-based life here, and how little our DNA separates us from those other life forms on this planet. And said, more than likely, it's that other life form is probably going to be carbon-based, but does it necessarily look like humans, this bipedal form that we're in? Maybe not. I mean, go look at the other life forms on this planet, like whales and dolphins and dogs and cats and birds, and they're all carbon-based. But would we ever encounter something that is non-carbon-based? That is the subject of much science fiction today, and I find it a fascinating thing. But it's possible. I won't say it's improbable or impossible, but I'd just say it's possible, because science is going to continue to surprise us. And I think something wonderful is still waiting to be discovered out there. And maybe one of the eventually, if it ever happens, we can make contact with another life form that is also sentient. But I think it'd be fascinating if it was something other than carbon. But you look at the statistics or just our understanding of chemistry today, it may not be.
That's very interesting. I'm given a question here. Let's read it out. This is from Jared, and it says, what do you think should be done or considered to manage our orbital environment for spacecraft launches? Do you think new technology will make this field more accessible to, I guess, citizen science efforts, so people who maybe aren't part of any proper scientific organization?
Yeah, I see what you're saying. Yeah. Of course, getting into space used to be the province of just two superpowers. the United States and the former USSR. And one of the chart, let me show you this. This is the satellite industry in context today, if you're still seeing my screen. And this tells you in context 2019 revenues in billions of US dollars. And we're approaching $400 billion annual for the space budget. And I don't know if this includes the classified space budget that the Department of Defense has, but this is where it's headed. Now, look at this chart. This is what you're facing. This is where your generation is headed. And I look at this, and there's this one area over here that talks about, on the right-hand side, the cislunar economy. This is from Bank of America Merrill Lynch, the global research in his basis on various resources. They see the cislunar economy headed for $2.7 trillion by 2045. And you talk to some other economists and they think it's going to be even higher than that. I call this the democratization of space, because you look up here to the upper left-hand side. I mentioned the US and USSR. This used to be just those two countries. Now you have over 80 countries now have satellites in space. And then you look at private companies that are moving into space with SpaceX orbiting Starlink. And then you look at some of these other companies, the Kuiper company wants to orbit its own space-based internet. And these other companies are moving up there. The question is, who's going to be the space traffic management cop? How are all of these satellites up there going to operate and not, one, run into each other, but also share the electromagnetic spectrum and communicate with their customers on the surface of the planet? And this issue continues to grow. And I think there have been, it's an issue that a number of countries around this globe are going to have to come to grips with. There's already the International Telecommunications Union in the United States. There's a Federal Communications Commission in which there is, I think it's a system that is begging for improvement on how people are applying for licenses today to use low Earth orbit or geosynchronous belt for satisfying space-based infrastructure for communications on the surface of the planet. And as more and more of these private companies and countries are able to exploit space, we're going to get into an issue of, one, dealing with debris, but also dealing with bandwidth. And those issues have to be addressed. And right now, neither one of those issues has been given to NASA to solve. One is not in the NASA charter. The US government has not told NASA to solve this. There are other within the United States government. I think the Department of Commerce has been given the stick for working on the space traffic management when it comes to debris control. And I think, I don't know where they are with their policies in developing this, but there's going to have to be an international agreement on how we're going to deal with this sooner than later, particularly if these things that are listed on this page are going to come true. It is an area that hopefully your generation will help us solve some of this stuff. But I think it's a problem that's begging for solutions today.
So we have a question from Ankit, and he's asking, what are the origins of the Kepler mission and how long was it running for?
God, that's a really good question. You guys have really good questions today. Bill Barucki, he's retired. And before COVID-19, I'd still see him in the office, and he still comes in because he's considered a fellow at NASA. He wrote the first paper on the Kepler. He didn't call it the Kepler mission at the time, but he wrote the first paper on the idea of using transit photometry to find planets in the Milky Way galaxy in 1984. And when he wrote that paper, people thought he was crazy. They said, bullshit, you can't do that. We don't have the instruments today. Well, later on, as technology improved, he started submitting one proposal after another, starting in the late 90s and early 2000s, proposing to NASA that we build this mission to go fly a space telescope that would be able to conduct the precision in transit photometry that Kepler needed to have to find the planets. And he was rejected time after time after time. And of course, when he was rejected, the board of NASA that was sending the rejection notices back were telling him and his team, you have to go solve these technical problems before we are able to approve this mission. Well, as technology continued to prove, he finally was able to demonstrate the technology on the ground that will enable a Kepler telescope to be developed and flown. So it was, as I mentioned earlier, it was 2009 when we launched the spacecraft, and he got approval earlier that decade to build the telescope. And so he's a study in perseverance and persistence. And that's what's required for even some of these missions, I think, that are going to be proposed in NASA in the future, because I see it happening. A lot of scientists come to NASA periodically proposing missions, and the boards, these people that are, the brainiacs that are, convened to review these missions, they tell them, you get to solve these certain technical problems before we, hand you a checkbook that says, go build this telescope, or go build this observatory, or go build this rover. That's how the system works. And but I got to hand it to Bill Baruchi, and I point to him sometimes to some of the college students that I talk with. If you want a role model, is some of the things that you want to do, you're going to have to persist and persevere and stick to it, because that's what he did, and that's what brought Kepler about. Bill Baruchi should be given a lot of credit for his persistence and his stubbornness as well, for making sure that the technological hurdles that he had to knock down were knocked down before NASA finally said, okay, we believe you can do this. And so they gave the approval and gave us a checkbook and said, go build it. We did.
So I have a question from Sogat, and he says, is the International Space Station retiring? And if it is, will it have any effect on the current time we're living in?
Yeah, it's there's some debate about that in this country. There are some people that want to retire it. It consumes and don't know the exact percentage, but it consumes a certain percentage of the NASA budget. And Congress keeps putting a lot of things on NASA's plate to go do. And in some cases we say, well, maybe we should turn the International Space Station over to private industry and let them run it. And then of course, there are some other congressmen and senators in the United States says, no, you guys should continue to run this thing because there's a lot of valuable science that can still be done with the International Space Station. I don't know where that's headed. There is the debate about it. And I think in many cases, this space station now is over 20 years old. And we still use it for a lot of things. And I think there's still a number of policymakers in the United States that want to continue to see it being used by NASA, while at the same time, there's others who want to turn it over to private industry. So it's a good question. I don't have an answer for it. I know that it's still under debate. It's still being discussed. And all I can say is stand by and we'll see where the policymakers and decision makers go with this.
Okay, I've got a question from Kartik, and I think what he's saying is, so the Kepler mission is finding these habitable planets in, I guess, areas of the Milky Way that are quite far away from us. And he's wondering, is it perhaps maybe better to focus on planets in our solar system that we could potentially try to establish some form of life on ourselves? Or do you think that there is any possibility of maybe being able to communicate with these further away planets in some way?
Well, getting there is a different problem. Discovering those planets turned out to be an easier task after we built Kepler, and now we understand the population of planets across the galaxy. Getting there is beyond our technical capabilities today. If you're a fan of Star Trek, yes, they got warp drive, but that's a fiction. We can't get there. That's Elon Musk. If you talk to him, he says it's incumbent upon the human species and our civilization to extend our reach beyond planet Earth, because and I'm fond of quoting him in this. He says, the future of the human species will bifurcate in one of two directions. We will remain a monoplanet species doomed to an extinction level event, or we'll become a multiplanetary species. And when he means that, is of course within our own solar system. There's, of course, there's organizations out there like the Breakthrough Foundation that want to come up with new technologies that will allow the in situ exploration of nearby systems like Alpha Centauri, but they have a lot of technological hurdles to overcome even in realizing their scientific objectives. One of the things that it still hits home for me, even after having observed all of the planets that have been discovered and confirmed by Kepler and TESS, is that we can't get to any of them. And we have only one that, and so there is no plan B. The planet we sit on is it. And so that's why I'm keenly interested in, when I participate in events like this one today, is carrying the torch of making sure that people understand the seriousness of climate change, and that it's still an addressable issue. We can still address it. There are some things that we're going to have to do to make that happen, but getting off fossil fuels as soon as we can is one of the things we should do. We now have the technology to enable us to move beyond that as our primary means of energy. But back to the question is, I think Elon Musk, of course, he looks at the world and the environment for the human species in a visionary way, as opposed to some others. And he has a vision. He wants to extend the reach of the human species because he's concerned about the human species remaining a singular planetary dwelling species. He wants to extend our reach because he wants to guarantee the survival of the human species. But I am also reminded of, when I hear him say that, of something that Carl Sagan once said. He says, extinction is a rule, survival is the exception. And it's like, which one is going to apply to us? It's a great question, but thank you.
So I think we'll probably wrap things up here, but we've got one more question from Sahin, and he asks, do NASA have plans to use the sun's energy or any other alternative energy sources in our solar system more efficiently or more closely, like the Dyson sphere?
Oh, that's a really good question, because there's one scientist who was on the Kepler mission, he's very renowned, and he got a grant. And I don't know who somebody gave him a grant to develop the software algorithms to look through the Kepler data to see if he could find a Dyson sphere. Which I was like, that would be amazing. And said, but you would have to ask, because I showed that animation very early today, which shows the planet crossing the face of its star, and you're watching the sunlight of the star dim as a result of the planet going across it. Now, what is the signature that you look for if you're looking for a Dyson sphere around a star? What is it that you look for? And I was asking this, and he says, I don't know, I have to think about that. And I said, but you got a grant to go look for this. Right now, NASA doesn't have plans for a Dyson sphere. I think that would be great. But we're not a type 1 civilization yet. You get to the point where you become a type 1 civilization, then you're far beyond our technical capabilities today. Nuclear power, that's what people look at today, and NASA still is investing in, we're investing in nuclear power again as a means for propulsion for our future spacecraft, for future missions. Of course, we have nuclear power plants on some of our deepest probes, Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, New Horizons. Every one of those spacecraft had a nuclear power plant on board, but that was for providing power to the spacecraft, not for propulsion. Now NASA is looking at nuclear power as a means of propulsion again. as a means to rapidly extend our reach into the solar system. But coming back to Kartik's question, we don't, we're investing in all kinds of amazing technologies, but building a Dyson sphere is beyond our reach right now. We had to develop some other technologies to allow us to do that, and we'd had to make many advancements, across our technical capabilities to do something like that. But we are, he spoke of solar cells and in using solar power, and we're becoming more efficient in the solar cells that we develop. And there's one I want to demonstrate within a year and a half, and it's called LISA T. It stands for Lightweight Integrated Solar Array and Antenna. And this thing, it fits inside, the first one is very small. It origamis into a 1U size CubeSat. And when it unfurls, you get 300 watts or more out of this tiny unfurled solar cell. So we're getting better at the solar cells we build, but getting to the infrastructure of a Dyson sphere, we're just not there yet. Maybe your generation will help bring that along.
Okay, well, thank you very much, Roger, for the extremely interesting talk. I'm sure that everyone has had many ideas and questions coming to their mind, and I'm sure everyone has been very inspired. I guess I just want to say to everyone who's watching, you can come along to our website and sign up to our organization. We're planning to run numerous events like this in the future. So if you just follow our social media channels or join our organization online, you can be kept informed of everything that we're doing. So yeah, again, Roger, thank you very much. And I think we can leave it there. And I've been told us to give our motto, which is "We are for science." So
that's a good motto. All right, thank you so much, Ryan, and thank you to BMUCO.
Thanks. Bye.
Bye-bye.
Thank you, sir.
Hello.